A circuit contains an ideal battery and four identical resistors arranged as shown in this circuit diagram. In part A, we just want to determine the equivalent resistance of the entire circuit in terms of R. That's where we start combining things in series and parallel and just see what we end up with if we could rewrite the whole thing as just one single resistor. So if you look at this diagram, the first thing you should note is that resistors B and C right here are in parallel because they share common endpoints. They both start at this point and they both end at this point. So let's combine B and C in parallel. And we could do that by using the parallel formula, which is you take the 1 over the reciprocals, 1 over the resistance, 1 over R plus 1 over R, which is equal to 2 over R, and then you take the reciprocal of that, so the equivalent resistance of B and C combined is R over 2. So let's redraw the circuit with B and C combined as one resistor. And now you'll see that it just becomes a simple series circuit where all three resistors are in series. So this is A, this is the BC combo. Remember we said the BC, the combination, is equivalent to R over 2. You may also remember from a previous video that I said whenever you have two resistors in parallel that are identical to each other, a simple way to do it is just cut it in half. And this basically just shows that. It's cut in half. And then that last resistor was the D. So this resistor and this resistor are both R. And then with this series combination, we just add them all together. So the equivalent resistance of the entire circuit, which is sometimes also referred to as the total resistance, or you might want to just say it as R, A, B, C, D, indicating all four resistors together. We just add R plus R over 2 plus R, and that's equal to 2.5 R, or 5 halves R. So that's the equivalent resistance for part A. Part B and part C are to rank the magnitudes of the potential difference and rank the magnitudes of the current. Now, since this is yet another circuit where all four resistors are the same, both rankings will have the same order. So when you have both questions like this, you can look at which one's easiest to solve. Is it easier to rank the potential difference, or is it easier to rank the current? And I think this one's very easy to rank the current because you can see that all of the current is coming out of the battery and going through resistor A. When it gets to this point, it splits, and it's going to split evenly since B and C are both the same resistance. So half will go this way and half will go this way. Then it comes back together at this junction, and all of that current flows back through resistor D. So you've already got your ranking right there, and a pretty simple way to explain it. And then you can go back to part B now and just say that the potential difference has the same ranking as the current because the resistors are all the same. In part D, we're now taking a resistor out of the circuit. So you can see that the new circuit in the diagram, basically you can just write it like this, because when that resistor, that one resistor B, is removed, it's impossible for any current to flow anywhere along that path, so you just treat it like that whole path is just missing. So the new circuit looks like this, which is just three resistors in series. So it's exactly the same as this, except now we have all three resistors have a value of R, whereas on this one, that second resistor, the middle resistor, was R over 2. So if we just label this as R, R, and R, and just add them together, the equivalent resistance of this circuit is just going to be 3R. F and G saying what's happening to the, E and F saying what's happening to the current and to the potential difference across A. So when we took out one of these parallel resistors, it increased the overall resistance of the circuit. We had originally 5 halves R, or 2.5 R. Now the circuit has increased in resistance to 3R. So since the overall circuit has an increase in resistance, that means there is overall less current coming out of the battery. So because there's slightly less current coming out of the battery, that means the current across resistor A has dropped. And since the current dropped, that means that the potential difference, you can also say, has gone down for part F. And then how does the current across resistor C change? So even though the overall current was less, the fact is that before, when it got to this point, it split with some current going this way and some current going this way. Now none of the current goes through B, so all of the current in the circuit will go through resistor C. So the current through resistor C has increased, and that means that the potential difference through across C will also have increased.